handy, of course, because we will refer to those a few times here, but interpreting pH curves is what we're going to look at today here. If you take a strong base, for example, sodium hydroxide and hydrochloric acid, what does the graph look like? Well, first of all, you have to, two things you have to know for sure here, guys, and this is very, very important. When they tell you that a strong base, when you're titrating a strong base with a strong acid, this right here, okay, that part right there, the second part of that statement, so you're going to titrate a strong base with the strong acid. That strong acid means that basically this second part here with this means that this is going to be in the burette, okay? And you need to know that for sure. Sometimes they'll give you a little clues, like if you look at the graph here, for example, you'll see that, of course, the volume of HCl as you go across the bottom here, that, of course, where's the volume going to come from? You're measuring out the volume every time kind of thing. That's going to be from the burette, okay? This means here, the titration of this base here is what we would call the aliquot. Yes, that's a term we use in Chem 20, hopefully, maybe. That's the part in the bottom. Okay, aliquot, A-L-I-Q-U-O-T. Now, they may not use that term because sometimes it's not commonly referred to that, but that's what it's called. Now, if I was going to draw a graph of this, just willy-nilly here, what would you expect to see? Where would I start the pH? Low or high here in this case? Or in the middle, 7. Where do I start? High or low? Low or high? Medium? High? Yes. Because, of course, titration with a strong base, this is in the bottom, this is in the burette. You can't measure the pH in the burette, right? The pH meter doesn't even fit in there. You know, the long skinny tube doesn't fit in there. So you got to measure at the bottom. So we're starting with the strong base on the bottom. So it's going to look something like this, yes? And you guys can see this from your graph that you guys did the other day. This was the first one that I did. This was the strong acid and strong base. And in fact, the only difference is we started low, right? I think on ours, and we ended up high, so this would be the opposite of that. What you're going to see here, well, actually, I probably should have did a little bit more of a, you're going to see a sharp rise or a sharp jump in this pH curve. Right in the middle here of that sharp rise or jump is what we would call the endpoint. Now, in Chem 20, the endpoint was something like, the endpoint, of course, is kind of the, neutralization, if you want, of the acid and the base, or is kind of that magical point where we get that 1 mole to 1 mole to relationship, okay? The endpoint in Chem 20 was probably a color change for you guys. For example, if we added phenolphthalein is quite often the one that we do, and it turns that light pink, remember? Yeah? And you try and get that lightest shade of pink, of course, and it's, everyone's like, is this too dark? And I'm like, well, red's too dark, yeah. Duh, right? No, but you know what I'm talking about. It's that light shade of pink. That's your endpoint. It's a sudden change of color. Well, in Chem 30, we could still do that. I mean, that's not an issue. We could still do that, but in Chem 30, what we did with this particular one here is that endpoint turns out to be not that sudden change of color, right? Because we didn't do indicators. We did neutralization, kind of strong acid, strong base. So in Chem 20, we would say that that's a pH of 7 in this particular case. Okay, and I'll explain a little bit more as we get to the bottom here. Okay, so that is what we call the endpoint. That's the kind of that's the perfect one-to-one relationship there. There's another term, and these are going to be given to you here in the next little bit here, but this here would be called something called the equivalence point. V, equivalence point. And that's the volume that was required to reach your endpoint. All right? And in Chem 20, it was the volume of the burette that you added to get to that light pink color. Well, on Thursday, it was the amount of volume, or the volume, that was required to get to the pH of 7. Now, you didn't hit 7 exactly, right? I doubt it. I mean, you could. It could happen, but it's probably very unlikely because, remember, you're adding 2 milliliters of acid, 2 milliliters of acid, 2 milliliters of acid, 2 milliliters of acid. Now, remember, in Chem 20, it's literally drops, right, that make the difference between clear and really too dark, right? If you go over just a little bit, it's too dark, yes? That's one drop difference. You're adding 2 drops, 2 milliliters, right? So you're adding quite a lot each time you do this, right? So the chance that you're going to hit a 7 exactly is probably not going to happen, all right? You're going to add 2, you're going to add 2, you know, if you kind of relate it back to Chem 20, you're going to add 2, it's going to be clear. You're going to add 2, it's going to be way too dark, okay? You've overshot it, basically, right? That's this sharp rise, sharp drop in a short amount of time, right? Like up here, for example, you had, you know, maybe in this case here, it'd maybe be a pH of 10 or something. You add 2 drops, and now all of a sudden you're down here and it's a pH of 6 or something like that, right? It goes quite drastically there, right? Because you've used too many drops basically to neutralize that perfectly. But then you do a nice little smooth curve and you say, where's about halfway on this sharp rise or drop here, and go over, and that would be of a pH of 7. What's that number equivalent to? And you could figure out the equivalence point from that, okay? And that's how you'd figure out the equivalence point when the pH is 7. By the way, a couple things here. When you do a strong base, let's say it's sodium hydroxide and hydrochloric acid, what are you actually doing? You guys need to write this down. Well, sodium hydroxide, if I was to predict the reaction of sodium hydroxide and hydrochloric acid, remember, this is the homework, of course. That's why it was important to do homework on Wednesday. If I was predicting what's the most likely reaction to take place here with the strongest acid and the strongest base, I'd say this is my strongest acid, this is my strongest base, and if I react the 2 together, that should give me basically the reaction that's taking place here. So H3O plus, yes, and hydroxide gives me strong acid, strong base, quantitative, 100%, right? Gives me 2 H2O liquids, okay? So basically as a product, when this is perfectly balanced, so when I have one of these reacting with one of these, and that happens at the equivalence point, basically the moles of this equals the moles of this at the equivalence point. When one of those reacts perfectly with one of those, I get water as a product. And water, okay, right here basically, this right here would be a product of water, okay? And that's why we talk about pH of 7, equal to 7, etc., etc. All right? So we're going to do lots of stuff with this today here, and that's kind of what we're going to set up here with to start with, okay? All right, let's move on here. So when you look at this graph here, the initial pH is much greater than 7 because the hydroxide ion concentration that you're measuring in the bottom of that solution, going back to this one here, of course, we're talking about this graph here. The hydroxide ion concentration, remember, you only start with hydroxide in the bottom, so the pH, of course, yeah, it's going to be like very high, right? Because we have a bunch of hydroxide in the bottom. And I'm going to start adding a little bit of acid, 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 until, of course, basically what happens is, when the HCl is added, the pH decreases as the added H3O plus reacts and neutralizes the hydroxide. So I'm neutralizing that hydroxide, some of it, some of it, some of it. Then all of a sudden what happens is you get an excess amount of H3O plus because I've added too much. That's when you kind of keep going to 30, 40, 50 milliliters. Add too much. And now the pH is quite low because now the reverse has happened. H3O plus is much greater. We have way more acid than we do the base. And that's this bottom part of the graph here. So that's this part here. We have way more acid than we have the base now. Okay? When those two equal each other, that's this right here. Okay? That's your end point, when those two are equal to each other. But once again, the chance of you actually hitting that number is probably not good. All right? It could happen if you get lucky. Okay? So that's what's happening there. The pH curve for a reaction between a strong acid and a strong base will always have a sharp jump or drop in pH. Any sharp change in pH indicates a quantitative proton transfer reaction has occurred. Basically means that 1 and 1 is reacted. Okay? The middle of this jump or drop is the titration's endpoint. So the middle of that drop or sharp rise is the endpoint, and the equivalence point is the volume required to reach that endpoint. Okay, make sure you know those two things, of course. And we labeled them on the graph for you, and we're going to do that over and over again here today. We're going to label those on the graph for you. Okay. It is proper. You should be able to predict an indicator that would kind of help you out with this. Measure that. That matches the reaction's endpoint. In grade 11, Chem 20, you guys did phenolphthalein. Probably was the most common one, that light clear to pink color. That's because technically we didn't do a strong acid and a strong base. You guys usually do acetic acid, and that's why we use that phenolphthalein indicator. And we'll talk a little bit about that as we go through here today. So let's take a look at this one here. These are all the things that I'm going to ask you guys to do for your homework today. It's going to be quite lengthy here for each one of these, but we're going to start with this. Okay, now this is, yes, pretty much the same question we just looked at, but let's talk about what I want you guys to do for this. So, first of all, let's write out an equation, I guess, for the reaction of hydrochloric acid and sodium hydroxide. So let's go ahead and do that. Predict a reaction. We're going to do good old-fashioned Chem 20 stoichiometry just like we've always done. So, to do a titration, of course, we did this earlier as well. Just a little bit of refresher here. You're going to write out the equation, put the information in the right spot, and remember, what am I trying to do here? I need to calculate the equivalence point. That's what I want to do. I want to find the volume required for this reaction to take place in this perfect one-to-one. So write out the equation first of all. Let's do that. Write out the equation. Put the information in the right spot. We'll start with that. Okay? We'll calculate the equivalence point, and we'll go from there. Okay, I always write down plus OH. I'm just going to leave it, but strong acid, strong base. Hydrochloric acid, H3O plus ions, chloride ions, yes. Sodium hydroxide, sodium ions, hydroxide ions, and of course this all takes place in water. This is, oh, sorry, don't forget the plus there. Strong acid, strongest base. So when I write this out, I should be writing out H3O plus aqueous and hydroxide aqueous gives me strong acid, strong base, quantitative reaction, one arrow, single arrow, 2 waters. Okay, we're going to put the information in the right spot. So we're going to look back. Let me grab my notes here so I can cheat a little bit here. So if you look back at the top there, you should see, okay, the information that you need to fill in here. So it says 50 milliliters of hydrochloric acid. This is good old-fashioned, straightforward stoichiometry, yes? 0.10 molar, so I'm going to put 0.10 molar, right? Remember, strong acid, so if I use 0.10 molar to start with, I get 0.10 molar H3O plus, yes? Okay, 50 milliliters of that, by the way. So I'm going to change that to liters. I do liters, you guys can do milliliters if you want. You have to make sure that if you're going to do liters, you got to do liters as well on the other side. If you're going to choose milliliters, that's okay. You're going to get milliliters on the other side. Please know what you're doing, okay? I do liters because I know that C and V has to be in liters, and I always stick with that. I've always done that way. But yes, milliliters works in this case, okay? So, and 0.20 molar sodium hydroxide. Remember, 0.20 molar sodium hydroxide would go there. 0.20 molar, if it's a strong acid, strong base means that if I have 0.20 molar sodium hydroxide, I have 0.20 molar sodium ions, 0.20 molar hydroxide ions, because it completely dissociates, right? So, look, I can find C and V, I can find N, that's 0.005 moles. I can move N over to here, remember this now? 0.005 moles. I have N, I have C, can I find V? Sure. N divided by C is how you find V, by the way. And I take N divided by C, I get 0.025 liters, or 25 milliliters, yes? Okay? What I've done here is I've told you, basically I've found the endpoint, okay? At 25 milliliters, or the equivalence point if you wish, whatever. endpoint to pH 7 equivalence point. This one here, for this particular graph, if I wanted to graph this, look, this, right, is the titrant, means basically that's going to be in the burette. What am I starting with in the bottom? It's got to be this here, 50 milliliters of 0.10 molar. Makes sense, doesn't it? Why would you put the 50 milliliters into the burette if they're telling you it's 50 milliliters? Right? The burette's purpose is to measure the volume. Well, I already got the volume, it's 50 milliliters, let's put that in the bottom, right? So, where's the pH going to start for this one? Low or high? Or medium? Low, medium, or high? Low, because you're starting with the acid in the bottom, right? So, you're going to start here, and sharp rise, and continue on. That's your equivalence point, your end point right here. In this case, we'll talk about that in a second. Your equivalence point is going to be right there, is your equivalence point. And in this case, we just found it to be, what, 25 milliliters, yes? So I'm going to write in here 25 milliliters, and of course it's in milliliters right there. This is your equivalence point. Okay? Now, look what happens when you mix a strong acid and a strong base. What do you get as a product? Huh? Water, right? Look, strong acid, strong base. This has a pH of 7, does it not? So, when I mix perfectly the right amount of acid and the right amount of base, the right amount of moles and the right amount of moles, look, that's going to be 7. Okay? When I have a perfect one-to-one relationship, I'm going to get exactly water, and that's it. So that pH would be 7 there. That would be my end point, of course. I'm kind of on an angle there. But that would be my pH of 7 there. If I want to pick an indicator for this, so when do I want to see that sudden color change if I wanted to use indicators? What would I pick? Well, you're going to go to your data booklet. Okay, do that now. You're going to need it today anyway. What would do a pH of 7 for you? What would do a pH of 7 for you? What's an option? There may be more than one option, by the way, and that's okay. What's probably your best one to start with, huh? Yeah, bromothiamyl blue would be a good one. Okay? And sometimes there's more than one option, guys, so keep that in mind. Bromothiamyl blue would be an option. I guess phenol red might be a second option. Yeah, I'd probably stick away from that one because it's got 2. So I probably wouldn't pick that one. Okay? So probably one of those 2. Okay? Are probably the most likely that I would pick. All right? So that's all the stuff that you're going to do, and you're also going to do one more thing for me. Can we find... We found basically the equivalence point, so we found out how much volume of sodium hydroxide was required to complete this titration. Could we figure out the initial pH of this solution before we start? What's the initial pH? Well, what are we starting with? What's in the bottom? What? What's in the bottom of the beaker? What are we taking the initial pH of? So guys, when we started at 0 the other day, you stuck a pH meter in the bottom, right? You recorded the number before you started. What's the initial pH for this one? It's what? HCl, yes? Hydrochloric acid. How much can we figure this out? Do we have the appropriate information for this? I hope so, because I'm going to ask you to do that. What's the initial pH of this solution? Well, it's of the hydrochloric acid, is it not? That's what's in the bottom. So, hydrochloric acid and water, of course. Remember, so there was some water to help make this solution, right? So that's the initial solution at the bottom, just hydrochloric acid and some water, right? The initial hydrochloric acid, the concentration was 0.10 molar of hydrochloric acid, yes? Hydrochloric acid, oh, sorry, I did it again. I get a little arrow happy here. That's wrong. That's better, right? Hydrochloric acid is a strong acid. So if I know that that's 0.10 molar, do I know the hydronium ion concentration? It is what? 0.10 molar. Right? Do I need Ka or Kb for this? Nope. Definitely not Kb. Please don't say that. This is an acid. So do I need Ka? No, because there isn't one, right? It's very large. Basically says it breaks up 100%. So can I figure out the pH of this? Sure. Negative log of 0.10 is 1. Yes? 1. 0.00. 2 significant digits because 2 in the question, yeah? 2 right there. There you go. That's your initial pH. That's what you would have started with. Okay? I mean, theoretically, that's what should happen in the lab. I mean, I don't know what concentrations we started with, actually, to be honest with you. I don't remember. We just mixed some stuff together. So, but if you go back up to here, okay, that would be a 1 pH solution that you start with. And then you'd start adding some hydroxide until basically you get to that magical point where the H3O plus and the hydroxide are in that perfect 1-to-1 relationship. And when that happens, it's a 1-to-1. Then we also know that that makes water, basically. 2 moles of water. It doesn't matter how many moles, but you get water. Water has a pH of 7, pure water. So we know that that's our end point. That's our equivalence point. It would take 25 milliliters to do that. Okay? Is that good? Any questions, anyone? Now that's a strong acid and a strong base, and we did some other ones, and we'll take a look at those. But any questions on that one? All pH curves will have this sharp rise or sharp drop. Whether it's a strong acid, strong base, weak acid, strong base, vice versa, it doesn't matter. They have this. And some have more, and we'll talk about that tomorrow, actually. Okay? But, good? Yes? So that's all I want. You're only getting 2 questions today because that's all the stuff that you need to do for each question. Okay? And a little bit extra as well. When a strong acid reacts with a strong base, the only products are water. H3O plus, of course, and the hydroxide gives you water. Therefore, the endpoint is 7. Okay? Well, what happens when it's not a strong acid, strong base? So here's what I want you guys to do. Take a look at this question. I want you guys to come up with the equation that goes with this question. Okay? Start putting information exactly what we just finished doing. Put information in the right spot. And I want you guys to solve for the equivalence point, just like we finished doing there. Okay, go ahead. Hydroxide. Okay. Strongest acid in this case, strong acid, strong base. Okay, both like the acid. So, double arrow, strong acid, strong acid, strong base, weak acid. Okay, this is your acid, this is your base, strong acid. Proton donor, proton receptor. Bronsted acid Lowry base, Bronsted Lowry acid base. Okay, I'm mixing up words today. Once again, you have all the information you need here. It says you got 20 milliliters of 0.16 molar. And you could find N from that information. You got a 0.20 molar solution here. Okay, and let me just move this up here. So C and V will give you N, which is 0.0032 moles. 0.0032 moles because it is a 1-to-1 relationship, of course, a 1-to-1 ratio. And in C, of course, we'll give you V, which works out to be 0.016 liters. All right. what would this graph look like? And it's important. And even if they didn't give you the bottom part here, you should be able to draw a graph of this, guys. Okay? So, very important here. Listen. Let's say they didn't even give you the bottom part there. Pretend this wasn't here for a second. If you want to draw a graph of this, you need to know what's going in the top, what's going in the bottom, because they may ask you that. So it's a titration of 20 milliliters. Well, pretty obvious in this case. Pretty obvious, I think, in this case here where that's going to go. I don't think that makes much sense putting that in the burette because it's 20 milliliters. Why would you put that in the burette, right? And this part, of course, once again, it's only 0.20 molar sodium hydroxide. So I assume, once again, that has to be, of course, that's your titrant, right? Is what we would call this, yes? Titrant. That means it goes in the burette. Okay, and this here would be your aliquot, means it goes in the bottom of your two options there. Okay, so what are you starting with in the bottom? Where should I start the pH? Low, high, medium? Low, high, medium. What do you think? Low, high, medium? Where's the pH meter going into? The aliquot, the bottom, right? That's the hydrocyanic acid, so we're going to start lower, yes? Less than 7. I don't know exactly where, but it's going to be less than 7. So somewhere down here. Now, with there is a little bit of a unique thing that happens with, by the way, with strong acid, weak bases, or vice versa. It doesn't kind of go quite the same. It's pretty close. Usually what you see is kind of just a little bit of a kind of start to rise here. So kind of just a little bit like that, and it kind of levels out, and then it does this. Okay? And once again, the number that we're looking for, the endpoint, is going to occur in this halfway in the middle here of this sharp rise. Once again, this would be your end point here. And down here, that would be, of course, your equivalence point. And your equivalence point in this case is what we just found, right? When HCN reacts exactly with 1 OH, okay, it takes 16 milliliters for that to happen. So it would take 16 milliliters here. We'd put that right there. 16 milliliters is your equivalence point, yeah?
So on the bottom of the volume, NaOH, if we have the milliliter scale, should we try to make 16 milliliters?
Yeah, I mean, it won't really matter what that is exactly. Like, they may have a detailed graph for you. Probably not. They might not even have any of that stuff on there for you. So it just depends. You can pretend it's 50 usually, yeah. But there's nothing to say it couldn't be 100 or even 200 for that matter. But usually we'd probably. Okay. Now, and there's your endpoint there. Okay, so there's kind of that there. Now let's take a look at this bottom part here for a second. We can calculate the initial pH too. We'll do that right away. But look here. Look, when I take a weak acid and a strong base, what do I get? Well, I get water. Yes. But what else did I get when I reacted those two together? What is CN minus? What's cyanide? It is a what? It's a weak base, right? So what we need to do now is, if I wanted to predict, is it going to be 7 where these two, well, not neutralized, but where these two, that endpoint, is it going to be 7 anymore? No. It's probably going to be, because look, when you get 1 and 1, right, perfectly, 1 and 1, gives you one of these and one of those. So yes, we did get water, but we also got a weak base as a result. So what you're going to have to do is kind of predict what that endpoint is. Now, there is a way to calculate that. We're not going to worry about that. We don't need to do that, right? We just don't need to worry about it. I'm not going to. So what you're going to get out is your data booklet. You're going to look on here, okay, and you're going to find all your acids and bases here. So look, as a result, CN minus is your weak base. Well, let's find that here. Where is your weak base? Where is CN minus here? It's pretty close to the bottom, isn't it? On the base side, yeah? Okay. Now remember, this isn't exactly, this is not your job. Okay, I'll kind of give you a ballpark here, but you know, it's not, they're not going to ask you a question on that. they'll have clear options for you. Okay, it's not going to be like, oh, I don't know, it could be this or this kind of thing. It's going to be only one option, right? Now look, the bottom right is hydroxide. That's your strongest base, right? So if we pretend that that pH, of course, if it was hydroxide, chances are it's going to be quite high pH, yes? Right, like 14, 13, somewhere in there. So that's 14 or 13 there. Look, water's at the other end. That's your weakest base, yes? Water has a pH of 7. So here's 7, there's 14. Where is Cn minus? Not too far away from 14, is it? Right? Now, I would probably reserve, you know, really strong bases for like 13, 14, maybe 12 even kind of thing. So where is this going to fall into? I would say Cn minus is about there somewhere. So in relation to the strongest bases, I would say it's going to have a fairly high pH. It's pretty close to hydroxide. So I'd say probably in the neighborhood of, when you think of 7 to 14, probably somewhere in the neighborhood of, now it's not, like I said, it's not a strong base, but it is one of the stronger, weaker ones. I'd say somewhere in the neighborhood of 10 to 11-ish probably, somewhere in there. Maybe 12, but somewhere there. And that's all you need to do. Approximately, I'd say 10 to 11, maybe even you might say 10.5 to 11.5, somewhere in there, whatever. Okay, it's somewhere there. Yes? Probably. So, you're going to approximate that, and like I said, the other options they're going to give you are going to be really low. Probably even 7 as an option, that's going to take care of one, and then probably maybe 2 that are like, you know, maybe 1 at 8 or something like that, and the other one will be acid, for example. Then, what indicator would be best suited for that pH range of 10.5, 11, 11.5, somewhere there? So what would that indicator be there? Well, let's see here. Oop, went the wrong way here. It would be what? What would be a good indicator there, guys? What do you think? You kind of want it in the middle there, right? So probably what? Alizarin yellow R, maybe? Yeah? I think would be a good indicator. Alizarin yellow R. Okay. What about anything else? Maybe indigo carmine might work. It's hard to say. Maybe even thymolphthalein might be an option. So, thymolphthalein. Maybe even indigo carmine. So once again, there's 3 options. Maybe you only need 2 options kind of thing. Maybe they're going to give you one of those options there. Okay, I'm telling you right now. They won't put all 3 of those on there and then pick something different. They wouldn't do that. But it's going to be one of those 3 answers probably. Okay? And once again, it kind of depends. Right? Okay? And there is a way to figure out the final pH, but like I said, that's nothing you need to worry about. Let's not worry about that. Okay, so that's how you need to do that. Can we calculate this right here? The initial pH. Once again, if you look at this graph here, guys, I would assume that we're going to take the pH of the acid, yes? I mean, that's what we're starting with here. Once again, when you look up to here, remember, this is what you are starting with in the bottom of the beaker. Can we figure out the initial pH of that? Sure we can. So let's do that. Initial pH. Now this is good old-fashioned review. That's why we're doing this. Initial pH. It's hydrocyanic acid in that beaker. So hydrocyanic acid, and of course we've mixed in some water, of course, to make that hydrocyanic acid. You'll get H3O plus and cyanide ions. Okay? We started with I believe it was a 0.16 molar, right? Now, this is a weak acid though, so I cannot simply just move that over, correct? It's not the negative log of 0.16, I'll tell you that right now. Okay? So, we're going to do a little x and x there. We're going to look up the Ka value for that. X squared over 0.16, right? And the Ka value for hydrocyanic acid is right there. 6.2 times 10 to the negative 10 is x squared over 0.16. We're going to figure out x here. I think I need a calculator for this one. I don't think I have this. So 0.2 times 10 to the negative 10 and 0.16. So x will be square root of that, of course. Yeah, 9.95 times 10 to the negative 6 moles per liter is what you'll actually get. So remember, Ka is the value that tells you how much it breaks up, right? That's what it is, a percentage. So when I start with 0.16 molar there, I actually only get 9.95 times 10 to the negative 6 moles per liter of hydronium ion. Not very many. Figure out the pH. I take the negative log of that. So the pH here would work out to be 5.00 actually. Exactly, 5.00. Okay. Now I can go back up to here and put in my 5.00. That's where this pH would start. Okay. So that would be the initial. That's what you guys would have done the other day. You would have started, you put the pH meter in. It would have been 0 before you added anything else. You started with the initial pH at 0 milliliters. That would have been 5. Yeah. 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 Okay. Good. Questions? Anyone else? Questions? Yes, no? Okay. All right. So, when a weak acid reacts with a strong base, products include water and a weak base. So, you're always going to get this kind of thing here. pH, of course, is going to be somewhere greater than 7. Really depends on the weak base that you make. Depends on the concentration you start with. Depends on many things. All right? So, we can estimate that. We don't need to worry about calculating it. Titration, let's do this one now. Last one, I believe. So let's go ahead and do this. Once again, write out all the information you think you need to have here, and we'll go with that. Okay, so list of ions or species that you need to have there for this. They kind of gave you this one here. This is the strongest base here, strongest acid here, of course. So reacting those two together, H3O plus, aqueous, OCl minus, aqueous. Remember, proton donor, proton acceptor, so HOCl aqueous, and water. Okay. It says here that we started with a 0.12 molar OCl minus ion with 0.20 here and 40 milliliters of this weak base here. So we can find N from that. I think it works out to be 0.0048. Is that right? I forget now. Let me just double check here. Yeah, 0.0048 moles. We'll move that over to here. 0.0048 moles, 1-to-1 ratio, right? V divided by 0.20, and we get 0.024 liters is your equivalence point. Now, once again, looking back up to here, guys, if we had to graph this, well, first of all, a key indication is right here, guys, right? Look, that's a volume of HCl, so that's obviously going to be in the burette. So are we starting high or low? Probably high, yes? Because, of course, the acid is in the burette. So we're going to start high. Usually what happens with these ones is, like I said, kind of dips down a little bit, and then drops like so. That right there is going to be your end point. And we'll come back to that in a second. I do know that my equivalence point is what I've just calculated, of course. This would be your equivalence point here. And that is, what did I say, 24 milliliters? 24 milliliters. Okay. What else? I think that's good. So far, anyway, going back to here for a second, notice once again, a pH is 7 here for that. And of course, HOCl is what? Acid or base? Acid. So we expect a pH of less than 7, right? This is a weak acid. So we have a pH of 7, yes, but we also have a weak acid present. So I would expect it to be less than 7 somewhere. Where exactly? Well, let's take a little gander here and see. Where's HOCl? It's pretty close to the bottom here, actually. Now remember, the strongest acids are at the top here, and as you work down, they get weaker and weaker. That's a pH of 0, let's say. That's a pH of water. Once again, pH of 7. Where's HOCl? It's pretty close to the bottom. So I'd expect this pH probably to be somewhere around, oh, I don't know. There's 7 there. That's 0. Probably 5 or 6, roughly, give or take a bit. So I would expect here, this would be approximately 5 to 6, or if you want, like maybe 4.5 to 5.5, somewhere in there, 5.5 to 6.5. Really depends, okay? But somewhere around there. I'd probably peg it as a pH of about 5-ish or so. What's an indicator that would work well with that? Well, let's take a look. Let's assume it's about 5-ish or so. Maybe 5 and, what did I say, 4.5 to 5 to 6, somewhere there. Let's see. Methyl red would probably be okay. Chlorophenol red would probably be okay. It would probably be 2 indicators that I would probably... Did we pick indicators for the last one? I forget now. We did? Okay. Probably something there. Okay. Yeah, probably one of those 2, I would say. And those are the, like I said, they'll pick one of those 2 and let you decide based on those. Okay? So that's kind of what you need to do for that one there. Once again, could we figure out that? Sure we can, right? That, of course, is your weak base in this case, or your base in this case. So what was the base? Well, the base is, of course, your hypochlorite, right? So let's figure out the initial pH. Well, that's your hypochlorite ion is what you start with, of course. So if I had the pH meter stuck in that aliquot there at the bottom, I would have it stuck in the hypochlorite solution. And of course, I would react that with water to give me some HOCl and hydroxide, right? And I know the hypochlorite ion concentration to start with. It is 0.12 molar. Once again, though, okay, I cannot just say that's a weak base, so I know it's not going to break up 100%. In fact, probably very little. That's not 0.12 mole, so I have to do this good old-fashioned thing here because it's a weak base. The second thing I'm going to have to do with this one, of course, is a little bit more involved with this one because I can't talk about Ka in this case, Kb, which is that, right? So I'm going to have to figure out the Kb value before I can continue on with this. So that, of course, will be 1 times 10 to the negative 14 over the Ka of hypochlorous acid 4 times 10 to the negative 8, which is actually 2.7. Is that right, somebody? Did somebody do that? Times 10, I better double check here. I forget what it is now. 2.7 or 2.5, don't remember now. Let's see. Oops. 2.5 times 10 to the negative 7. Okay. So that's the Kb value there that you're going to use instead. Because remember, we're talking about base, not an acid here. So once again, just like before, Kb is going to be x squared over 0.12 molar. My Kb value is 2.5 times 10 to the negative 7. X squared over 0.12. So I'm going to calculate x. So 0.12 times 2.5 times 10 to the negative 7. By the way, is it okay if I do the approximation with this? Is 0.12 1,000 times bigger than 2.5 times 10 to the negative 7? I think we're okay, eh? So once again, that's probably going to happen for you, right? Like I'm telling you it's probably going to happen, it's going to happen. Square root. And I get right here 1.73 times 10 to the negative 4 moles per liter. Now, I'm going to take the negative log of that, okay, and I get about 3.76. Don't forget, that's POH, yes? Thanks. That's POH, that's not pH. So once again, 14 minus that, and we should get 10.24 as a final answer. 2 significant digits there because that's what we started with in their question. Okay? So we started out at approximately a pH of 10.24. It neutralized probably around a pH, or sorry, I shouldn't say neutralized, but it basically reached our equivalence point roughly about 5-ish, 5.5, somewhere in there, maybe somewhere in that 5 to 6 or 4.5 to 6 range there kind of thing. Okay? And that's where it neutralized basically. All right? So that's all the stuff that we want you to be able to do. Start the initial pH. You can do it in any order you want. I don't care, but you're going to have to do a graph. Initial pH, calculate the equivalence point, approximate the pH that at the end point, all right, and pick indicators that do that for you. Okay? So don't forget. Once again, when you take a weak base and react it with a strong acid, the products include a water and a weak acid, of course. All right? Therefore, the endpoint will be lower than 7. All right? And multiple choice questions on diploma could be just as simple as, you know, if I take this and this, what would you expect the endpoint to be? Right? And they might say less than 7, equal to 7, greater than 7, and come up with some other number, I don't know, as a different option. So, you know, once again, you kind of just have to know, you know, when you take once again, you have to be able to write out the reactions, right? Strong acid. And if they just give you a generic question, strong acid and a weak base, well, pick one, right? If you can't remember that a strong acid and a weak base gives you water and a weak acid, okay, and if you don't know that, then pick some. Pick a strong, everyone knows hydrochloric acid is a strong acid, pick that. Pick a weak base from your data booklet, react the two together, see what you get. You get water and a weak acid, okay? So just think about things like that, okay? All right, we got some questions here for you. Like